There is a law in physics that has never been broken, not once, not in any experiment ever conducted, not in any observation ever recorded, not in any corner of the universe ever examined. The law says this: information cannot be destroyed. The total information content of a closed system is conserved. The present always contains a complete record of the past. The laws of physics are reversible. If you know the state of the universe now, you can, in principle, reconstruct the state of the universe at any previous time. Nothing is ever truly lost. Nothing is ever truly erased. Every event leaves an indelible mark on the fabric of reality, a mark that can never be removed, only scrambled, redistributed, hidden, but never destroyed. This law is called unitarity. It is the most fundamental structural principle of quantum mechanics, the most precisely tested theory in the history of science. Every prediction quantum mechanics has ever made relies on it. Quantum computing relies on it. The standard model of particle physics relies on it. The theory of quantum electrodynamics, which predicts the anomalous magnetic moment of the electron to more than 12 decimal places of accuracy, relies on it. Unitarity is not a minor feature of quantum mechanics. It is the load-bearing wall of the entire edifice. And at the center of every black hole, according to our best theory of gravity, this law is violated. Information dies. The quantum state of everything that falls into a black hole, every particle, every photon, every atom, every bit of data, every memory, every trace of every event, is compressed into the singularity, a point of infinite density and zero volume, where the equations of general relativity produce infinity, where the mathematics breaks down, where the physics ceases to function. And when the black hole eventually evaporates through Hawking radiation, the radiation is thermal, featureless, carrying no information about what fell in. The information is not hidden. It is not scrambled. It is gone, destroyed, erased from the universe forever. This is the death of information at the singularity. And it is, without exaggeration, the most important unsolved problem in all of physics. Because if information can be destroyed, if unitarity can be violated, if the past can be truly erased, then the foundations of quantum mechanics are cracked. The most successful theory in the history of science is wrong. And everything built on top of it, the standard model, quantum field theory, quantum computing, quantum information science, all of it rests on a cracked foundation. The scope of the problem is cosmic. According to current scientific estimates, the observable universe contains roughly 100 billion galaxies. Nearly every large galaxy harbors a supermassive black hole at its center. The Milky Way alone may contain hundreds of millions of stellar mass black holes. The nearest known black hole is roughly 1,600 light-years away. These objects are not exotic rarities. They are common features of the celestial landscape. And at the center of every single one of them, according to general relativity, information is dying. The quantum records of everything that ever crossed their event horizons are being compressed into singularities and destroyed. If this is correct, the universe is hemorrhaging information. The cosmic ledger is being erased, line by line, across billions of locations simultaneously. Right now, at the center of our galaxy, Sagittarius A star, a supermassive black hole with roughly 4 million solar masses, is consuming information. Stars, gas, dust, photons, gravitational waves, everything that crosses its event horizon is carried toward the singularity. The information encoded in all of that matter, the precise quantum state of every particle, is being processed, scrambled, and, according to the classical theory, destroyed. The same is happening at the center of every galaxy in the observable universe. There are, according to current scientific estimates, on the order of 100 billion galaxies, each harboring at least one supermassive black hole. Hundreds of millions of stellar mass black holes populate each galaxy. The universe is filled with information-destroying machines, running constantly, consuming the quantum records of everything that falls within their reach. By the end of tonight, you are going to understand why general relativity predicts the death of information at the singularity, why quantum mechanics says this cannot happen, why the resolution of this conflict has consumed the attention of the world's greatest theoretical physicists for more than 50 years, and what the leading proposals for saving information look like. You are going to confront the possibility that the singularity does not exist, that information is preserved through mechanisms we are only beginning to understand, and that the resolution of the information paradox will reveal the deepest truths about the nature of space, time, and reality. Before we get started, if you find these mysteries as fascinating as we do, take a second to like the video or subscribe. It is a simple action, but it helps this channel reach more curious minds like yours. The death of information at the singularity is not just a problem about black holes, it is a problem about the nature of reality. It is a problem about whether the universe keeps perfect records or whether the records can be destroyed. It is a problem about whether the past is permanent or whether it can be erased. It is a problem about whether the laws of physics are truly reversible or whether irreversibility lurks at the center of the most extreme objects in the cosmos. The answer to this problem, whatever it turns out to be, will reshape our understanding of physics at the most fundamental level. The information that is consumed includes not just the quantum states of individual particles but the correlations between them, the entanglement that links distant systems, the phase relationships that encode interference patterns, the entire web of quantum connections that makes the universe a coherent whole. The death of information at the singularity is not the death of isolated facts. It is the death of connections, of correlations, of the web of relationships that constitutes the quantum state of the universe. Now, let us begin. To understand the death of information at the singularity, we must first understand what information means in physics, how it is encoded, how it is preserved, and why its destruction would be catastrophic. Because information, in the physicist's sense, is not what most people think. It is not knowledge, it is not meaning, it is not data in the everyday sense. It is something deeper, more fundamental, more indestructible, and more intimately connected to the structure of reality than any colloquial notion of information can capture. In physics, information is the complete specification of the quantum state of a system. The quantum state contains everything there is to know about the system, the positions and momenta of all particles, their spins, their charges, their entanglement relationships, their phases. Every detail, every nuance, every correlation. The quantum state is the ultimate description. Nothing is left out, nothing is approximate. The quantum state is the system, described with complete precision. Unitarity is the principle that the quantum state evolves reversibly. The Schrödinger equation, the fundamental equation of quantum mechanics, is deterministic in both directions. If you know the quantum state now, you can calculate the state at any future time, and you can calculate the state at any past time. The evolution is a rotation in a mathematical space called Hilbert space, and rotations are reversible. No information is lost, no information is gained. The total information content is conserved, exactly, always, without exception. This is not an abstract mathematical nicety. It has concrete physical consequences. Conservation of probability is a consequence of unitarity. The fact that the probabilities of all possible outcomes always add up to 1, no more, no less, is guaranteed by unitarity. If unitarity fails, probabilities can leak. They can add up to more than 1 or less than 1. The predictions of quantum mechanics become inconsistent. The theory self-destructs. The classical analogue of information conservation is Liouville's theorem, which states that the volume of phase space is conserved under Hamiltonian evolution. In classical mechanics, the state of a system is a point in phase space, and the evolution of the system traces a trajectory through phase space. Liouville's theorem says that the volume occupied by a cloud of initial conditions is preserved as the cloud evolves. The cloud may be stretched and folded and distorted, but its volume never changes. Information, encoded in the phase space volume, is conserved. In quantum mechanics, the analogue is the conservation of the von Neumann entropy of a pure state. A pure state has 0 von Neumann entropy, and unitary evolution preserves this. A pure state always evolves into another pure state. It never evolves into a mixed state, a state of reduced information, a state of increased entropy, without the involvement of an environment. This is the quantum version of information conservation. Now, general relativity enters the picture. General relativity, published by Albert Einstein in 1915, is a classical theory of gravity. It describes gravity as the curvature of spacetime caused by mass and energy. It is not a quantum theory. It does not incorporate quantum mechanics. It does not respect unitarity. It does not conserve information in the quantum mechanical sense. And when general relativity is applied to the most extreme gravitational configurations, black holes, it produces the singularity, a point where the physics breaks down and where information is, apparently, destroyed. The concept of entropy provides the bridge between information theory and physics. In information theory, entropy measures the uncertainty about the state of a system. A system with high entropy has many possible states, and specifying which state it is in requires a lot of information. In thermodynamics, entropy measures the degree of disorder. The second law says entropy never decreases. The arrow of time is the direction of increasing entropy. The connection between these two concepts was established by Claude Shannon in 1948 and extended by Edwin James and others. Information entropy and thermodynamic entropy are the same quantity, measured in different units. A physical system with high thermodynamic entropy is one that requires a lot of information to specify. A physical system with low entropy is one that requires little information. The total information content of the universe, measured by its entropy, is a physical quantity, as real and as measurable as energy or momentum. Black holes have the maximum entropy for a given mass. The Bekenstein-Hawking entropy of a solar mass black hole is roughly 10 to the power of 77, vastly exceeding the entropy of any other object of comparable mass. A solar mass quantity of ordinary matter, such as a star, has an entropy of roughly 10 to the power of 57. The black hole has 10 to the power of 20 more microstates than the star. This enormous increase in entropy tells us that the information about the internal structure of the matter has been enormously increased by the collapse. The matter has gone from a relatively simple configuration, a star, to an enormously complex configuration, a black hole, with 10 to the power of 20 times more possible internal states. This vast increase in entropy is not a destruction of information, it is a scrambling of information. The information about the original star is still there, in the black hole, but it has been distributed across 10 to the power of 77 microstates in a pattern of unimaginable complexity. The information has not been erased. It has been encrypted, scrambled, hidden, distributed, but it is still present. The death of information occurs, according to the classical theory, when the black hole evaporates. The Hawking radiation that carries away the mass and energy of the black hole is thermal. It carries no information about the specific microstate of the black hole. When the evaporation is complete, all that remains is a cloud of thermal radiation with zero information about the original star. The 10 to the power of 77 microstates have been converted into a single featureless thermal state. The information has been destroyed. The Hawking temperature of a black hole is inversely proportional to its mass. For a solar mass black hole, the temperature is roughly 60 billionths of a Kelvin. For a black hole with the mass of the Earth, roughly 10 to the power of 23 kilograms, the temperature would be roughly 1/10 of a Kelvin. For a black hole with the mass of Mount Everest, roughly 10 to the power of 15 kilograms, the temperature would be roughly 10 to the power of 11 Kelvin, hot enough to emit gamma rays. The smaller the black hole, the hotter it is, and the faster it evaporates. The final moments of evaporation are explosive, the black hole shrinking and heating in a runaway cascade that ends in a burst of high-energy radiation. The evaporation time depends on the cube of the mass. A solar mass black hole evaporates in roughly 10 to the power of 67 years. A black hole with the mass of the Moon evaporates in roughly 10 to the power of 48 years. A black hole with the mass of a mountain evaporates in roughly 10 to the power of 17 years, about the current estimated age of the observable universe. The smaller the black hole, the shorter its lifetime. But even the shortest-lived black holes take far longer than any human timescale to evaporate. The evaporation process is extraordinarily slow because the Hawking temperature of astrophysical black holes is far below the temperature of the cosmic microwave background, roughly 2.7 Kelvin. As long as the cosmic microwave background is warmer than the black hole absorbs more energy from the background than it emits through Hawking radiation. It gains mass rather than losing it. Only after the universe has cooled sufficiently, many trillions of years from now, according to current models, will astrophysical black holes begin to evaporate in earnest. The first exact solution to Einstein's field equations was found by Karl Schwarzschild in 1916. Schwarzschild's solution describes the spacetime around a non-rotating, uncharged, spherical mass. At the Schwarzschild radius, an event horizon forms, a boundary from which nothing can escape. At the center, a singularity forms, a point of infinite density and zero volume. The singularity is not a place in spacetime. It is the boundary of spacetime. Geodesics, the paths of particles through spacetime, terminate at the singularity. They do not pass through it. They do not continue beyond it. They end. The spacetime itself ceases to be defined, and with it, the information encoded in the quantum state of any particle that reaches the singularity ceases to exist. Roger Penrose proved in 1965 that singularities are unavoidable consequences of general relativity under very general conditions. His singularity theorem requires only that general relativity is correct, that energy density is positive, and that a trapped surface has formed. Once these conditions are met, geodesic incompleteness follows. Worldlines must terminate. The singularity must exist. Stephen Hawking extended Penrose's methods and proved more general theorems. Together, the Penrose-Hawking singularity theorems established that singularities are ubiquitous in general relativistic spacetimes. Every black hole contains a singularity. Every singularity is a place where information, according to classical general relativity, is destroyed. In 1974, Stephen Hawking discovered that the situation is even worse than the singularity alone would suggest. Hawking showed that black holes emit thermal radiation, now called Hawking radiation, due to quantum effects near the event horizon. Virtual particle-antiparticle pairs are separated by the extreme curvature. One particle falls in, the other escapes. The black hole loses mass. Over unimaginably long timescales, the black hole evaporates. The Hawking radiation is thermal. It has a temperature, the Hawking temperature, inversely proportional to the mass of the black hole. For a solar mass black hole, the Hawking temperature is roughly 60 billionths of a Kelvin, far colder than the cosmic microwave background, at roughly 2.7 Kelvin. The evaporation time for a solar mass black hole is roughly 10 to the power of 67 years. For supermassive black holes, the evaporation time stretches to 10 to the power of 100 years. These are timescales far beyond any meaningful human comprehension. But the thermal nature of the radiation is what matters for information. Thermal radiation is featureless. It carries no information about what fell into the black hole. A black hole formed from the collapse of a star made of hydrogen emits exactly the same Hawking radiation as a black hole of identical mass formed from a star made of iron, or from a collection of books, or from a fleet of spaceships. Every detail of the infalling matter is erased. The radiation knows nothing about the origin. If the black hole evaporates completely and the radiation carries no information, then all the information that ever crossed the event horizon is permanently lost. The quantum state of everything that fell in is destroyed. The past has been erased. The universe no longer contains any record of what happened. Unitarity is violated. This is the black hole information paradox. Hawking posed it in 1975, and it has consumed the attention of theoretical physicists ever since. Hawking himself initially believed that information was genuinely destroyed. He argued that the singularity does destroy information, that unitarity is violated in the presence of black holes, and that quantum mechanics must be modified to accommodate this violation. He made a famous bet with John Preskill, wagering that information was lost. In 2004, Hawking conceded the bet, acknowledging that information is likely preserved. But the concession did not explain the mechanism. How is information preserved when the classical theory says it is destroyed? Where does the information go? How does it escape the singularity? These questions remain among the deepest in physics. The gravitational redshift observed in accretion disks provides direct evidence for the extreme conditions near the event horizon. Light emitted from the inner regions of the disk is redshifted by the intense gravitational field, its frequency reduced. Ion emission lines from accretion disks have been observed with extreme redshifts consistent with emission from within a few Schwarzschild radii of the event horizon. These observations confirm that matter does fall toward the event horizon, carrying its information content with it. The gravitational waves detected by LIGO, Virgo, and Cagra from merging black holes provide another window. Each merger produces gravitational waves at specific frequencies, determined by the masses and spins of the merging black holes. The ring-down phase, when the merged black hole vibrates, tests the no-hair theorem. Roughly 90 gravitational wave events have been observed. Each one confirms that the exterior of black holes obeys general relativity with high precision. None tells us what happens to information at the center. The Event Horizon Telescope photographed the shadow of M87 star in 2019 and Sagittarius A star in 2022. The shadow is the silhouette of the event horizon against the glowing accretion disk. The size and shape match the predictions of general relativity. The images confirm that event horizons exist and that their external properties are as predicted, but the images tell us nothing about the interior or the fate of information at the singularity. Andrea Ghez and Reinhard Genzel shared the Nobel Prize in 2020 for tracking individual stars orbiting Sagittarius A star for more than 2 decades. Their measurements confirmed the mass and compactness of the central object, establishing beyond reasonable doubt that it is a supermassive black hole. The stars orbit at speeds up to several thousand miles per second, confined by the gravitational field of the black hole. The information encoded in those stars, if they were to fall in, would be consumed by the event horizon and carried toward the singularity. The relationship between the no-hair theorem and the information paradox is particularly illuminating. The no-hair theorem states that the exterior of a black hole is described by just 3 numbers, but the Bekenstein-Hawking entropy says the interior has 10 to the power of 77 microstates. The gap between 3 exterior numbers and 10 to the power of 77 interior states is the information paradox in miniature. Where is the information? It cannot be in the exterior, which is described by 3 numbers. It cannot be at the singularity, which has 0 volume. It must be on the horizon, encoded in the holographic record, distributed across the 2-dimensional boundary in patterns of quantum entanglement, so complex that no exterior measurement can decode them. The information is there, but it is hidden so thoroughly that it appears to be absent. The membrane paradigm, developed by Kip Thorne and collaborators in the 1980s, provides a physical model for the information-storing properties of the horizon. In this framework, the event horizon behaves like a physical membrane with viscosity, electrical conductivity, and temperature. The membrane absorbs, processes, and re-emits information. It is not a passive boundary but an active processor, a hot surface that scrambles and redistributes the quantum correlations of everything that falls through. The history of the information paradox is a history of escalating crises and deepening insights. Hawking's 1974 paper on black hole radiation was initially greeted with skepticism. Many physicists doubted that black holes could emit radiation, but the calculation was quickly confirmed by independent methods, and the reality of Hawking radiation became widely accepted. The information implications took longer to appreciate. Hawking himself drew the conclusion explicitly in a 1976 paper, arguing that black hole evaporation violates quantum mechanical unitarity. The reaction was sharply divided. Some physicists accepted the conclusion and explored its implications. Others rejected it, insisting that unitarity must be preserved, that some mechanism, yet to be discovered, must return the information to the outside universe. The debate between the information destroyers and the information preservers lasted for decades. On one side, Hawking and his allies argued that the singularity genuinely destroys information and that quantum mechanics must be modified. On the other side, Susskind, 't Hooft, Preskill, and their allies argued that information must be preserved and that the semi-classical approximation is misleading. Gerard Hooft proposed in 1993 that the maximum information content of any region of space is proportional to the area of its boundary, not its volume. This was the holographic principle, the idea that the three-dimensional world is encoded on a two-dimensional boundary. Leonard Susskind developed this idea further. If the holographic principle is correct, the information that falls into a black hole is encoded on the event horizon, not compressed into the singularity. The information does not die because it never reaches the singularity. It is on the surface. Maldaceno's 1997 discovery of the ADS CFT correspondence provided the strongest evidence yet that information is preserved. The correspondence showed that a gravitational theory in the bulk of anti-de Sitter space is exactly equivalent to a non-gravitational quantum field theory on the boundary. The boundary theory is manifestly unitary. It preserves information automatically. If the two theories are equivalent, the bulk theory must also preserve information. This was the turning point. After Maldacena, the weight of evidence shifted decisively toward information preservation. Hawking conceded his bet in 2004. The question shifted from whether information is preserved to how it is preserved. The Bekenstein-Hawking entropy provides a crucial clue. In the early 1970s, Jacob Bekenstein argued that black holes must have entropy proportional to the area of the event horizon. Hawking's calculation of the radiation temperature confirmed this, establishing the precise formula. The entropy equals 1/4 of the horizon area in Planck units. For a solar mass black hole, this entropy is roughly 10 to the power of 77. The entropy tells us that the black hole has an enormous number of internal microstates, roughly 10 to the power of 10 to the power of 77 distinct configurations. These microstates must somehow encode the information about what fell in. The information is not destroyed in the quantum picture. It is encoded in the microstates of the black hole, scrambled beyond recognition but still present. The challenge is to explain how this encoded information eventually escapes through the Hawking radiation, which appears to be thermal and featureless. The no-hair theorem states that a black hole is characterized by only three quantities: mass, charge, and spin. This radical exterior simplicity contrasts with the enormous interior complexity implied by the entropy. The exterior says three numbers, the interior says 10 to the power of 77 microstates. The gap between these two descriptions is the information paradox in miniature. Where is the information? How is it encoded? And how does it escape? The scales involved are staggering. Consider the information content of a single human body, roughly 10 to the power of 28 atoms, each with quantum properties including position, momentum, spin, and entanglement relationships. All of this information, if you fell into a black hole, would be consumed by the singularity according to general relativity. Every atom, every molecule, every cell, every memory, every aspect of your identity, compressed into the singularity and, if Hawking's original analysis is correct, erased from the universe forever, not hidden, not encrypted, erased. Now multiply this by every star, every planet, every photon, every gravitational wave that has ever fallen into any black hole in the universe. The information content of entire stellar systems, entire molecular clouds, entire star-forming regions, all consumed, all processed, all potentially destroyed. The death of information at the singularity is not a minor bookkeeping problem. It is a cosmological catastrophe, threatening the informational integrity of the universe itself. The connection between information and entropy is illuminated by the concept of coarse-graining. When we describe a physical system using macroscopic variables like temperature, pressure, and volume, we are coarse-graining the description. We are ignoring the microscopic details, the precise positions and momenta of every particle, and tracking only the average macroscopic properties. The entropy measures how much information is lost in this coarse graining, how many microscopic states are compatible with the observed macroscopic state. A black hole represents the ultimate coarse graining. The no-hair theorem says the macroscopic description of a black hole requires only three numbers: mass, charge, and spin. But the microscopic description, the complete specification of all internal microstates, requires 10 to the power of 77 numbers for a solar mass black hole. The gap between the macroscopic simplicity and the microscopic complexity is the entropy. The information is the entropy. And the question of whether the information dies at the singularity is the question of whether the entropy is genuine, whether the microstates are real, whether the microscopic description has physical content. The history of black hole thermodynamics provides the context for this question. In 1972, Jacob Bekenstein proposed that black holes have entropy proportional to the area of the event horizon. His argument was based on a thought experiment involving lowering a box of thermal radiation toward a black hole. If the black hole had no entropy, the total entropy of the universe would decrease when the box fell in, violating the second law of thermodynamics. Bekenstein concluded that the black hole must have entropy, sufficient to compensate for the entropy of the infalling radiation. Hawking initially opposed Bekenstein's proposal, arguing that if black holes had entropy, they would have temperature, and if they had temperature, they would radiate, and black holes cannot radiate. Then Hawking discovered that black holes do radiate. His own calculation confirmed Bekenstein's proposal and established the precise entropy formula: S equals A over 4 in Planck units. The formula is remarkable for several reasons. First, it connects gravity through the area of the horizon to thermodynamics, through the entropy to quantum mechanics, through the Planck units. It sits at the intersection of the three great frameworks of physics. Second, it assigns an enormous entropy to black holes, far exceeding the entropy of any other object of comparable mass. Third, it implies that the black hole has an enormous number of internal microstates that must encode the information about everything that fell in. The question of whether these microstates are real, whether they have a microscopic accounting, whether they can be counted explicitly from a fundamental theory, is one of the central questions of quantum gravity. String theory has provided an explicit counting for certain classes of black holes, matching the Bekenstein-Hawking formula exactly. This counting, first performed by Andrew Strominger and Kamran Vafa in 1996, was one of the most important results in string theory. It demonstrated that the microstates are real, that they can be counted, and that their number matches the thermodynamic entropy. The Strominger-Vafa counting applies to highly simplified, supersymmetric black holes that are far from the astrophysical black holes we observe. Extending the counting to realistic black holes remains an open problem. But the result established the principle: black holes have microstates. The microstates encode information, and the information is preserved. The no-hair theorem creates a tension with the microscopic picture. The theorem says the exterior of the black hole carries only 3 numbers. The microstates say the interior carries 10 to the power of 77 configurations. How are the 10 to the power of 77 microstates compatible with the 3-number exterior? The answer, according to the holographic principle, is that the microstates are encoded on the event horizon, not in the interior. The horizon is not featureless. It is a dense encoding of information, a holographic record of everything that fell in, compressed onto a 2-dimensional surface. This encoding is what the Hawking radiation must eventually read out. As the black hole evaporates, the information encoded on the horizon is transferred to the radiation through subtle quantum correlations. The transfer is slow, taking roughly the Hawking evaporation time, but it is complete. By the end, all the information has been transferred. The death of information has been averted. The detailed mechanism of the transfer remains unclear. The island formula tells us that the transfer happens. The page curve tells us when it happens. The Hayden-Preskill protocol tells us how fast individual bits can be recovered. but the precise physical process by which the information moves from the horizon to the radiation is not yet understood. This is one of the most important open questions in quantum gravity. The process of accretion provides a vivid picture of how information is consumed by black holes. Matter spiraling inward through the accretion disk is heated to millions or billions of degrees by friction. The innermost regions glow in X-rays. The disk can outshine the entire host galaxy. Up to roughly 40% of the rest mass energy is converted to radiation before the matter crosses the event horizon. This is the most efficient energy source in the universe. Active galactic nuclei, quasars, and blazars are all powered by this process. But once the matter crosses the event horizon, the information it carries is hidden from the outside universe. The quantum states of every atom, every electron, every photon in the infalling matter are concealed behind the one-way boundary. The accretion process is the feeding of the information-destroying machine. The event horizon is its mouth, the singularity is its stomach, and the Hawking radiation is its waste product, thermal and featureless, carrying no memory of what was consumed. The Blandford-Znaigeck process adds another dimension. Magnetic fields threading the ergosphere of a rotating black hole can extract rotational energy and launch relativistic jets from the poles. These jets extend for hundreds of thousands of light years, carrying energy extracted from the black hole's rotation. The jets are powered by the ergosphere, the region just outside the event horizon where spacetime is dragged by the rotation. The energy in the jets comes from the rotation, not from the information content of the black hole. The information remains inside, hidden, potentially dying at the singularity. The number of black holes in the observable universe provides a sense of the scale of the information crisis. The Milky Way alone may contain hundreds of millions of stellar mass black holes. The observable universe contains roughly 100 billion galaxies. Each galaxy harbors a supermassive black hole and potentially hundreds of millions of stellar mass black holes. The total number of event horizons is staggering, trillions of trillions, each one consuming information, each one hiding quantum records behind a one-way boundary. The total entropy of all black holes in the observable universe is estimated at roughly 10 to the power of 104. The total entropy of all non-black hole matter is roughly 10 to the power of 88. The entropy of the universe is overwhelmingly dominated by black holes. The information processing of the universe is overwhelmingly dominated by black holes. If information dies at the singularity, the universe is hemorrhaging information on a cosmic scale. Then, something happened that changed everything. The core problem of the death of information at the singularity is not merely that information is lost, it is that the loss violates the most fundamental principle of the most successful theory in the history of science. And the attempts to resolve this violation have revealed that the problem is far deeper, far more interconnected, and far more transformative than Hawking originally imagined. The information paradox is not just about information, it is about the nature of space, time, reality, and the fabric of the universe itself. To appreciate the depth of the crisis, consider what unitarity actually implies. If the quantum state of a system at one time uniquely determines the state at all other times, past and future, then the universe is a perfect record keeper. Nothing that ever happened can be truly erased. The arrangement of atoms in your body right now, in principle, contains a complete record of the arrangement of atoms at any previous time, all the way back to the earliest moments. The universe is, in this sense, a perfect memory. Every event is permanent. Every detail is preserved. The past is not gone. It is encoded in the present, distributed across the quantum correlations of every particle in the cosmos. The singularity threatens to erase this record. If matter falls into a black hole and reaches the singularity, and if the singularity is a genuine physical point of infinite density where the quantum state is destroyed, then the record is broken. The present no longer contains a complete record of the past. The past has been truly erased. The universe has developed amnesia. The consequences cascade through all of physics. If unitarity fails at the singularity, it might fail elsewhere. If information can be destroyed by gravitational collapse What prevents information from being destroyed by other extreme processes? The precedent is set, the principle is violated, the door is opened. And once the door is opened, the entire structure of quantum mechanics, which depends on the perfect preservation of information at every step, is undermined. Hawking's original argument for information loss is deceptively simple. The Hawking radiation is produced by quantum effects in the vicinity of the event horizon. The radiation depends only on the properties of the horizon, its area, its temperature, its surface gravity. It does not depend on the details of what fell into the black hole. The radiation is thermal, characterized entirely by its temperature, carrying no information about the specific microstate of the black hole. If the black hole evaporates completely, the final state is pure thermal radiation, a state of maximum entropy and minimum information. The initial state, whatever it was, has been converted into a final state that contains no record of the initial state. Information is lost. But here is the problem. This argument treats the gravitational field classically, while treating the matter fields quantum mechanically. Hawking's calculation is semi-classical. It uses quantum field theory on a fixed classical spacetime background. The background spacetime, including the event horizon and the singularity, is not quantized. It is treated as a fixed, given geometry. The quantum effects of gravity are ignored. If the gravitational field is quantized, if spacetime itself is a quantum object with its own quantum fluctuations and its own quantum states, then the semi-classical approximation breaks down at the singularity, where the curvature reaches the Planck scale, and if the approximation breaks down, the conclusion drawn from it, that information is destroyed, may also break down. The death of information at the singularity may be an artifact of the semi-classical approximation, not a feature of the full quantum theory. This is the key insight that has driven 50 years of progress on the information paradox. The death of information is predicted by a classical theory applied to a quantum situation. A fully quantum theory might preserve information. The question is, how? The Heisenberg uncertainty principle provides a direct argument against the death of information at a true singularity. At the singularity, matter is compressed into zero volume. This means positions are known with infinite precision, but the uncertainty principle says infinite precision in position implies infinite uncertainty in momentum, which implies infinite kinetic energy and infinite pressure resisting further compression. Quantum mechanics forbids the compression to zero volume. The singularity cannot form in the way general relativity predicts. The collapse must halt at the Planck density, roughly 5.1 times 10 to the power of 96 kilograms per cubic meter, and if the singularity does not form, information is not destroyed there. The Planck scale is the natural scale of quantum gravity. The Planck length is roughly 10 to the power of negative 35 meters. The Planck time is roughly 10 to the power of negative 43 seconds. The Planck density is roughly 5.1 times 10 to the power of 96 kilograms per cubic meter. At these scales, the classical description of space-time breaks down and quantum gravitational effects dominate. The gap between the Planck scale and our experimental capabilities is vast, roughly 17 orders of magnitude. No experiment can probe the Planck scale directly. The fate of information at the singularity must be determined through theory. The thermodynamic argument against information death is compelling. The Bekenstein-Hawking entropy assigns a finite, well-defined entropy to every black hole. The Hawking temperature is finite and well-defined. The four laws of black hole mechanics are precise and consistent. A true singularity, where information is destroyed and physics breaks down, is thermodynamically ill-defined. The finite, consistent thermodynamics of the exterior demands a finite, consistent interior. The death of information, which would create a thermodynamically ill-defined state, is inconsistent with the well-defined exterior thermodynamics. The third law of thermodynamics requires that entropy be well-defined at all achievable states. A singularity violates this requirement. The Bekenstein-Hawking formula assigns entropy to every black hole. If the singularity destroyed information, the entropy would be undefined at the moment of destruction. This is inconsistent with the formula. The thermodynamics demands that information survive. The cosmic censorship conjecture, proposed by Roger Penrose in 1969, states that singularities are always hidden behind event horizons. If cosmic censorship holds, the death of information at the singularity is hidden from the outside universe. The outside universe never sees it. The event horizon serves as a shield, protecting the cosmic information balance from the catastrophe at the center, but the shield is temporary. When the black hole evaporates, the shield disappears, and if the information has been destroyed, the destruction is revealed. This is why the evaporation process is so important for the information paradox. While the black hole exists, the death of information is hidden behind the horizon. You could argue that the information is merely hidden, not destroyed, and that the ledger is balanced as long as the black hole exists. But when the black hole evaporates completely, the horizon disappears, the hiding place is gone, and the question becomes unavoidable: where is the information? If the information is in the Hawking radiation, encoded in subtle quantum correlations, then information is preserved. If the information is not in the radiation, then it is gone, and unitarity is violated. The Page curve, which describes the entropy of the radiation as a function of time, distinguishes between these two possibilities. If the entropy follows the Page curve, information is in the radiation. If it does not, information is lost. And it gets worse, because even within the semi-classical framework, the problem is not as simple as Hawking originally presented. Don Page pointed out in 1993 that if information is preserved, the entropy of the Hawking radiation must follow a specific curve, now called the Page curve. The entropy rises during the first half of the evaporation, as the radiation becomes more entangled with the remaining black hole. Then, at a specific time, called the Page time, roughly the halfway point of the evaporation process, the entropy begins to decrease. By the time the black hole has fully evaporated, the entropy of the radiation has returned to zero. The radiation is in a pure state, containing all the information that originally fell in. The Page curve is the signature of unitary evolution. If the entropy of the radiation follows the Page curve, information is preserved. If it does not, information is lost. For decades, no one could calculate the entropy of the Hawking radiation precisely enough to determine whether it follows the Page curve. The semi-classical approximation which Hawking used predicts that the entropy rises monotonically and never decreases. This is the thermal answer, the information-destroying answer. The question was whether a more precise calculation, incorporating quantum gravitational effects, would give the Page curve instead. The answer came in 2019 and 2020, with the island formula. But, before we get to that resolution, we must understand the full depth of the crisis. Because the information paradox is not one problem, it is many problems, nested inside each other, each more disturbing than the last. The first nested problem is the question of where the information goes. If information is not destroyed at the singularity, where is it? The no-hair theorem says the exterior of the black hole carries no information beyond mass, charge, and spin. The Hawking radiation appears thermal and featureless. The interior is hidden behind the event horizon and terminates at the singularity. There seems to be nowhere for the information to hide. The second nested problem is the question of when the information escapes. If information is eventually returned in the Hawking radiation, when does it start to come out? The Page time is roughly the halfway point of evaporation, but the semi-classical approximation says no information escapes at any time. The information cannot begin to escape until quantum gravitational corrections modify the semi-classical result. And quantum gravitational corrections are expected to be important only at the Planck scale, at the very end of the evaporation process. How can information begin to escape at the Page time, which is vastly earlier than the Planck time of the evaporation? The third nested problem is the question of how the information is encoded in the radiation. Even if information is preserved, the early Hawking radiation appears thermal. How can thermal-looking radiation carry information? The answer involves subtle quantum correlations between early and late radiation. correlations so delicate and so distributed that they are invisible to any local measurement. The information is encoded holographically, spread across the entire radiation field, accessible only through extremely complex measurements that correlate widely separated quanta. The information is there, but it is hidden in the most thorough way quantum mechanics permits. The fourth nested problem is the scrambling time. How quickly does the black hole process the information that falls in? Patrick Hayden and John Preskill showed in 2007 that black holes are the fastest scramblers in nature. For Sagittarius A star, the scrambling time is on the order of milliseconds. Within thousandths of a second of crossing the horizon, the information has been processed, scrambled, and distributed across the entire horizon. The black hole saturates the fundamental quantum bound on scrambling speed, the limit set by the Margulis-Levitin theorem. The fifth nested problem is the firewall paradox, introduced in 2012 by Ahmed Almhiri, Donald Marolf, Joseph Polchinski, and James Sully. The AMPS argument showed that three cherished principles cannot all hold at the event horizon of an old black hole, one that has radiated away more than half its entropy. Unitarity requires that the late Hawking radiation be maximally entangled with the early radiation. The smooth horizon requires that the Hawking radiation be maximally entangled with the interior. But the monogamy of entanglement forbids a quantum system from being maximally entangled with two different systems simultaneously. One entanglement must break. If the interior entanglement breaks, the smooth horizon is replaced by a firewall. If the exterior entanglement breaks, unitarity is violated. The connection between the information paradox and the structure of quantum entanglement is one of the deepest aspects of the problem. The smooth vacuum state at the event horizon is maintained by entanglement between modes just inside and just outside the horizon. This entanglement is what makes the horizon feel smooth and unremarkable to a crossing observer. If this entanglement is disrupted, the vacuum is disrupted, and the horizon becomes a firewall of high-energy radiation. The monogamy of entanglement is the key constraint. A quantum system can be maximally entangled with, at most, one other system. The late Hawking radiation must be maximally entangled with the early radiation to preserve information, as Page showed. But it must also be maximally entangled with the interior to maintain the smooth horizon, as the equivalence principle requires. Both cannot hold simultaneously. One entanglement must break. If the interior entanglement breaks, the smooth horizon is destroyed. A firewall forms. The falling observer is incinerated rather than crossing smoothly. The death of information at the singularity is avoided, but at the cost of the death of the observer at the horizon. If the exterior entanglement breaks, information is lost. Unitarity is violated. The death of information is real. The AMPS firewall argument crystallized this dilemma in 2012. It showed that the information paradox is not just about the singularity, it is about the event horizon itself. The crisis extends from the center to the boundary. The death of information at the singularity and the nature of the event horizon are intimately connected. Resolving one requires resolving the other. The Penrose process and the ergosphere of rotating black holes add thermodynamic constraints. Energy can be extracted from the ergosphere. The four laws of black hole mechanics mirror the four laws of thermodynamics. Any resolution of the information paradox must be consistent with these thermodynamic laws. The consistency requirements constrain the mechanism by which information is preserved. The scrambling time, milliseconds for Sagittarius A star, tells us how fast the black hole processes information. The Margulis-Levitin theorem sets the maximum speed. Black holes operate at this limit. The death of information at the singularity is avoided because the black hole processes information, not destroys it. The singularity is not an incinerator, it is a processor. The fastest processor in nature. The Penrose process and the ergosphere of rotating black holes reveal that black holes are dynamic thermodynamic systems. Energy can be extracted from the ergosphere. The four laws of black hole mechanics mirror the four laws of thermodynamics exactly. The zeroth law says surface gravity is constant. The first law relates mass, area, angular momentum, and charge changes. The second law says area never decreases classically. The third law says surface gravity cannot be reduced to zero in finite steps. These laws constrain any resolution of the information paradox. Any mechanism for information preservation must be consistent with the thermodynamic properties of the black hole. The exterior thermodynamics, with its finite temperature and finite entropy, demands a finite and well-defined interior structure. A singularity that destroys information is inconsistent with this demand. The Bekenstein-Hawking entropy formula, S equals A over 4 in Planck units, is the Rosetta Stone connecting gravity, thermodynamics, and quantum mechanics. It tells us the number of internal microstates, it tells us the information content, and it tells us that the information is on the surface, proportional to area, not in the volume. The holographic nature of the entropy is a powerful clue about where the information resides and how it is preserved. The connection between information preservation and the arrow of time is one of the deepest aspects of the problem. The arrow of time is the direction of increasing entropy. Entropy is an informational quantity. If information is destroyed, the entropy counting becomes ambiguous. The second law becomes ill-defined. The arrow of time becomes uncertain. The preservation of information is necessary not just for quantum mechanics but for the coherence of thermodynamics itself. The unitarity argument against information death can be stated simply. Quantum evolution is a rotation in Hilbert space. Rotations are reversible. The quantum state at one time uniquely determines the state at all other times. If information is destroyed at the singularity, this reversibility fails. The quantum state at one time does not uniquely determine the state at all times. Unitarity is violated, and with it, the entire structure of quantum mechanics, which depends on unitary evolution at every step. The Page curve provides the definitive test. If the entropy of the Hawking radiation follows the Page curve, rising during the first half of evaporation and falling during the second half, information is preserved. If it rises monotonically, information is destroyed. The island formula showed that the gravitational calculation produces the Page curve. Information is preserved. The scrambling time quantifies the speed of information processing. For Sagittarius A star, milliseconds. For a solar mass black hole, microseconds. The black hole processes information at the maximum rate permitted by quantum mechanics. The death of information would require that this maximum rate processor somehow fails at its task. But the Hayden-Preskill result shows that the processor succeeds. Individual bits can be recovered after one scrambling time. The processor works. Information survives. The firewall paradox brought the information crisis to its sharpest point. It showed that preserving information at the event horizon comes at a cost. The destruction of the smooth interior predicted by general relativity. The death of information and the death of the smooth interior are, in a sense, complementary. You can save one or the other, but perhaps not both. The Bekenstein-Hawking entropy, proportional to the horizon area, constrains any resolution. The entropy of a solar mass black hole is roughly 10 to the power of 77. Any mechanism that preserves information must be consistent with this entropy. It must account for 10 to the power of 77 microstates. It must explain how these microstates encode the information and how the information eventually escapes. The four laws of black hole mechanics, established by Bardeen, Carter, and Hawking, mirror the four laws of thermodynamics. Black holes have genuine temperature and genuine entropy. The thermodynamic framework constrains the information dynamics. Any resolution of the paradox must reproduce the thermodynamic properties, the Hawking temperature, the Bekenstein-Hawking entropy, the four laws. The connection between the information paradox and the structure of quantum gravity is deep and unavoidable. Every approach to quantum gravity must resolve the paradox. String theory resolves it through fuzzballs and microscopic counting. Loop quantum gravity resolves it through quantum bounces. The holographic principle resolves it through boundary encoding. The resolution of the information paradox is a necessary condition for any theory of quantum gravity. If a proposed theory does not preserve information, it is wrong. This makes the information paradox one of the most powerful tools for constraining quantum gravity theories. We cannot directly probe the Planck scale. We cannot build an accelerator powerful enough to test quantum gravity directly, but we can use the information paradox as a consistency check. Any theory that fails to preserve information during black hole evaporation is ruled out. This is an extraordinarily stringent constraint, and it has shaped the development of every major approach to quantum gravity. The connection between the information paradox and the emergence of spacetime is equally deep. If spacetime is emergent, arising from quantum information and entanglement, then the death of information would undermine the emergence. The fabric of spacetime would unravel. The geometric description would fail not just at the singularity but everywhere. The preservation of information is necessary for the continued existence of spacetime. This is the deepest argument against information death. The universe cannot afford to lose information, because information is what the universe is made of. The connection between the information paradox and the arrow of time is also profound. The arrow of time is the direction of increasing entropy. Entropy is an informational quantity, measuring the number of microstates compatible with the macroscopic description. If information is destroyed, the counting of microstates becomes ambiguous. The entropy becomes ill-defined. The arrow of time becomes uncertain. The preservation of information is necessary for the well-defined directionality of time. The Penrose-Hawking singularity theorems guarantee that within classical general relativity, singularities are unavoidable, but the theorems do not apply to quantum gravity. They require the positivity of energy, a condition that may be violated by quantum effects at the Planck scale. They require the existence of a trapped surface, which is a classical concept that may be modified by quantum corrections. The theorems guarantee that information dies in the classical theory. They do not guarantee that information dies in the quantum theory. The quantum energy conditions, which describe how quantum fields can violate the classical energy conditions under certain circumstances, provide a concrete mechanism by which the singularity theorems can be evaded. Quantum fields can have negative energy densities in certain states, violating the positive energy condition that the singularity theorems require. If these violations are sufficiently strong near the would-be singularity, the formation of the singularity can be prevented. The collapse halts, the density reaches a maximum, and information survives. The connection between the information paradox and the concept of the black hole interior is subtle and important. The interior, the region behind the event horizon, is where the information is processed. The scrambling dynamics occur in the interior. The approach to the singularity occurs in the interior. The death of information, if it occurs in the interior. But the holographic principle says the interior is not fundamental, it is emergent, it is a projection of the boundary physics. If the interior is emergent, then the death of information in the interior is an emergent phenomenon, a feature of the projection, not of the fundamental theory. This perspective resolves the paradox in the most radical way possible. Information does not die because the place where it would die, the singularity, is not fundamental. The singularity is a feature of the emergent geometric description. When the geometric description breaks down, the singularity dissolves. And the information, which was never at the singularity in the fundamental description, is preserved on the boundary, encoded in the holographic record, accessible through the quantum correlations of the Hawking radiation. The connection between the information paradox and quantum computing is one of the most productive intersections in modern science. The study of information processing in black holes has driven advances in quantum information theory, quantum error correction, and quantum computational complexity. The Hayden-Preskill protocol, the scrambling time, the fast scrambling conjecture, the computational complexity of decoding the Hawking radiation, all of these results have applications in quantum computing that extend far beyond black hole physics. The scrambling dynamics of black holes have inspired the development of random quantum circuits as models for quantum chaos. The connection between scrambling and thermalization has illuminated the process by which isolated quantum systems reach thermal equilibrium. The fast scrambling conjecture, which states that black holes saturate the fundamental bound on scrambling speed, has provided a benchmark for quantum information processing that no other system can match. Something is wrong with our assumptions. Not a small adjustment, not a minor correction. Something deep and fundamental about the way we think about information, space-time, and the singularity must change. The death of information at the singularity is not a failure of quantum mechanics. It is a failure of our understanding of gravity at the quantum level, and resolving this failure will require a revolution. The relationship between the information paradox and the emergence of spacetime represents the deepest implication of the entire program. If spacetime is emergent, arising from quantum information and entanglement, then information is more fundamental than spacetime. The death of information would not merely violate unitarity. It would undermine the very existence of spacetime. The fabric of space and time is woven from information. Destroying information would be like pulling threads from the fabric. The geometric description would unravel. This is the deepest argument against information death. The universe cannot afford to lose information because information is what the universe is made of. The death of information at the singularity would be the death of the substrate from which spacetime emerges. The singularity would not merely be a point where physics breaks down. It would be a point where reality itself is compromised. The holographic principle makes this explicit. The three-dimensional bulk spacetime is a projection of two-dimensional boundary physics. The boundary physics is informational. The bulk geometry is generated by the entanglement structure of the boundary quantum state. If the entanglement is disrupted, the bulk geometry disconnects. If the information is destroyed, the entanglement is disrupted. The death of information would cause the death of spacetime. Mark van Ramsdonk showed in 2010 that reducing entanglement causes spacetime to disconnect. This result establishes the direct connection between information and geometry. Spacetime exists because information exists. Spacetime is connected because information is entangled. The preservation of information is the preservation of spacetime. The error-correcting structure of holographic spacetime provides the mechanism by which information is protected. The bulk spacetime is encoded in the boundary through a quantum error-correcting code. The code is redundant. Local errors, including the singularity, can be absorbed by the code without destroying the information. The information survives because the code protects it. The gravitational path integral, which sums over all possible spacetime geometries, provides additional evidence. When replica wormholes are included in the sum, the result is finite and unitary. The singularity is washed out. Information is preserved. The full quantum theory, which includes all geometries, preserves information, even though individual classical geometries contain singularities. The Penrose-Hawking singularity theorems guarantee singularities within classical general relativity, but the theorems do not apply to quantum gravity. The classical theorems guarantee the death of information in the classical theory. They do not guarantee it in the quantum theory. And every candidate for quantum gravity preserves information. The Heisenberg uncertainty principle forbids compression to zero volume. The quantum pressure halts the collapse at the Planck density. The singularity does not form. Information does not die. The classical prediction is overridden by quantum mechanics at the Planck scale. The thermodynamic constraints are equally powerful. The Bekenstein-Hawking entropy is finite. The Hawking temperature is finite. The four laws are well defined. A singularity that destroys information is thermodynamically ill-defined. The thermodynamics demands information preservation. 3. Every principle of quantum mechanics, from the uncertainty principle to unitarity to the thermodynamic laws, points in the same direction. Information does not die at the singularity. The classical theory is wrong at the center. The quantum theory, whatever its precise form, preserves information perfectly. But here is what makes this truly terrifying. We cannot observe the singularity. We cannot probe it. We cannot experiment with it. The event horizon hides it from view. Everything we know about the death of information at the singularity comes from theory, and the theories, for 50 years, have been unable to agree on the answer. The information paradox has attracted the most creative and determined theoretical physicists in the world for more than half a century. The proposals they have developed span the entire landscape of theoretical physics, from string theory to loop quantum gravity to holographic duality to quantum information theory. What follows is a journey through the most important proposals, each offering a different perspective on whether information truly dies at the singularity, and, if not, how it is saved. The first proposal is Hawking's original position. Information is genuinely destroyed. Hawking argued that the singularity represents a true breakdown of physics, that the quantum state is destroyed at the point of infinite density, and that unitarity is violated during black hole evaporation. In this view, the death of information is real. Quantum mechanics must be modified to accommodate it. The laws of physics are not perfectly reversible. The universe does not keep perfect records. The past can be truly erased. This position had significant support in the early years of the paradox, but it has fallen out of favor for several reasons. First, modifying unitarity is not a minor adjustment. It requires changing the most fundamental mathematical structure of quantum mechanics, with consequences that cascade through all of physics. Second, the holographic principle and the ADS CFT correspondence, developed in the 1990s, provided strong evidence that information is preserved in black hole evaporation. Third, Hawking himself conceded in 2004. The second proposal is black hole complementarity, introduced by Leonard Susskind, Lars Thorlacius, and John Uglum in 1993. Complementarity states that the description of the black hole from the outside and the description from the inside are both valid but complementary. The outside observer sees information processed on the horizon and returned in Hawking radiation. The falling observer sees information falling through the horizon toward the singularity. Both are correct. Neither is complete, and no single observer can verify both, because the event horizon prevents communication from inside to outside. In the complementarity picture, information does not die at the singularity. It is returned in the Hawking radiation. From the outside perspective, the death of information is an artifact of trying to combine the inside and outside descriptions into a single global picture. From any single observer's perspective, information is preserved. The paradox arises only from the illegitimate attempt to combine perspectives that cannot be simultaneously verified. Complementarity was widely accepted for nearly 2 decades. It appeared to resolve the paradox elegantly. But the firewall argument of 2012 exposed a flaw. The AMPS paper showed that complementarity, as originally formulated, is inconsistent with the monogamy of entanglement for old black holes. Complementarity remains an important idea, but it requires modification. The third proposal is the fuzzball program, developed within string theory by Samir Mathur and collaborators. In the fuzzball picture, the singularity does not exist. The entire interior of the black hole is replaced by a complicated structure of strings and branes. There is no event horizon in the traditional sense. There is no singularity. There is no place where information dies. Each fuzzball configuration is a different microstate of the black hole. The number of microstates matches the Bekenstein-Hawking entropy. For a solar mass black hole, this is 10 to the power of 77. Each microstate radiates differently from the fuzzball surface, carrying information about the specific configuration. Information is preserved from the outset. It never enters a singularity because no singularity exists. The numbers are striking. The fuzzball program provides a microscopic accounting of the Bekenstein-Hawking entropy, matching the macroscopic formula exactly for certain classes of black holes. This is one of the most important achievements of string theory. It demonstrates that black holes have microstates, that these microstates are countable, and that their number matches the thermodynamic entropy. The death of information is avoided because each microstate evolves unitarily and radiates information through its surface. The loop quantum gravity approach to the information paradox offers a different perspective. In loop quantum gravity, spacetime is discrete at the Planck scale, composed of quanta of geometry. The singularity is replaced by a quantum bounce. The matter that collapses to form the black hole reaches maximum density at the Planck core and bounces outward. The black hole eventually transitions to a white hole, from which the matter and information re-emerge. In this picture, Information does not die at the singularity because the singularity does not exist. It is replaced by a region of Planck-scale physics where the discrete quantum geometry halts the collapse. The information passes through the Planck-scale bottleneck and re-emerges on the other side. The death of information is avoided because the information has a path through the center, a temporal bridge from collapse to expansion. The work of Hal Haggard and Carlo Rovelli, published in 2014, explored this transition in detail. The Planck star, a compact object at the Planck density, serves as the bridge between the black hole and the white hole. The matter bounces at the Planck star and begins to expand. The information that fell in during the collapse is carried through the bounce and released during the expansion. The timescale for this transition, as seen by an external observer, may be very long, potentially comparable to the Hawking evaporation time. But the transition does occur, and when it does, the information is released. The death of information is not permanent, it is temporary. The information is temporarily hidden in the Planck-scale core and eventually released through the white hole transition. The causal set theory approach, developed by Raphael Sorkin and others, proposes that spacetime is fundamentally discrete, a partially ordered set of events connected by causal relations. In a discrete spacetime, the point-like singularity of general relativity cannot form. The collapse reaches a maximum density determined by the fundamental spacing of the causal elements. Information is preserved because the discrete structure prevents the formation of the singularity. Asymptotically safe gravity, initiated by Steven Weinberg in 1979, provides yet another perspective. The gravitational coupling approaches a finite fixed point at high energies. The extreme curvatures near the singularity are tamed. The infinite density is replaced by a finite value. The death of information is avoided because the singularity is smoothed out by quantum effects. The convergence of all these approaches on the preservation of information is the most powerful theoretical evidence available. String theory says information survives through fuzzballs. Loop quantum gravity says it survives through quantum bounces. Holographic duality says it survives through boundary encoding. Causal set theory says the singularity never forms. Asymptotic safety says the curvature is bounded. The gravitational path integral says replica wormholes ensure unitarity. Every approach, from every direction, arrives at the same conclusion: information does not die. But the fuzzball program has limitations. Explicit fuzzball geometries have been constructed only for highly simplified, idealized cases. Extending the construction to realistic astrophysical black holes remains an open problem. And the fuzzball predicts that a falling observer encounters the fuzzball surface before crossing the would-be horizon, violating the equivalence principle of general relativity. The fourth proposal comes from the holographic principle and adds CFT. Juan Maldaceno's 1997 discovery of the ADS CFT correspondence showed that a theory of gravity in anti-de Sitter space is exactly equivalent to a quantum field theory on the boundary of that. Spacetime. The boundary theory is manifestly unitary. It preserves information automatically. If the bulk theory is equivalent to the boundary theory, then the bulk theory must also preserve information, even during black hole formation and evaporation. In the ADS CFT framework, the death of information at the singularity is impossible. The boundary theory has no singularity. It has no event horizon. It evolves unitarily for all time. Whatever appears as a singularity in the bulk must correspond to something smooth and well-defined on the boundary. The death of information is an artifact of the bulk geometric description, not a feature of the fundamental physics. Maldaceno's paper has been cited tens of thousands of times, making it the most cited paper in the history of high-energy physics. Within this framework, the Bekenstein-Hawking entropy is exactly the logarithm of the number of boundary microstates. The page curve is automatically satisfied because the boundary evolution is unitary. Information is preserved because the boundary theory preserves it. But ADS CFT applies to anti-de Sitter space, which has a negative cosmological constant. Our universe has a positive cosmological constant. Whether holographic duality extends to our universe is an open question. The most powerful tool for proving that information survives operates in a universe that is not ours. The fifth proposal is the island formula, developed in 2019 and 2020 by Netta Engelhardt, Ahmed Al-Mahiri, Jeffrey Pennington, Henry Maxfield, Thomas Hartman, Juan Maldacena, Edgar Shagulian, and Amir Hossein Tajdini. The island formula represents the most significant recent breakthrough in the information paradox. It showed, through gravitational calculations, that the entropy of Hawking radiation follows the Page curve. Information is preserved during evaporation. The key ingredient is the quantum extremal surface, a generalization of the classical extremal surface that includes quantum corrections. Before the Page time, the quantum extremal surface is empty, and the entropy of the radiation rises, as Hawking predicted. After the Page time, a new quantum extremal surface appears, an island, a region of the black hole interior that is informationally connected to the radiation rather than to the black hole. The island contributes negatively to the entropy, causing it to decrease. The total entropy follows the Page curve. The island formula gives us the answer. Information is preserved. But it does not give us the mechanism. It tells us what the entropy does. It does not tell us how the information physically escapes from the black hole. It is a result without an explanation, an outcome without a process. The death of information is averted, but the mechanism of its salvation remains mysterious. The sixth proposal is ER equals EPR, put forward by Susskind and Maldacena in 2013. This conjecture states that quantum entanglement and wormholes are the same phenomenon. Every pair of entangled particles is connected by a microscopic Einstein Rosen bridge. The smooth event horizon is maintained by a wormhole network connecting the interior to the exterior. Information does not die at the singularity because it is connected to the exterior through the wormhole network of entanglement. If ER equals EPR is correct, the singularity is not a dead end for information. It is a hub of wormhole geometry, a point of maximum connectivity linked to the outside through the entanglement structure of the Hawking radiation. Information flows through the wormholes. It does not die. It is redistributed through the quantum geometry of entanglement. The connection between information preservation and the nature of spacetime is perhaps the most important implication of the entire program. If information is more fundamental than spacetime, then the death of information would be worse than a violation of unitarity. It would be the destruction of the substrate from which spacetime emerges. The fabric of space and time is woven from quantum information. Destroying that information would be like pulling the threads from the fabric. The geometric description would fail not just at the singularity, but everywhere. This is the deepest reason why physicists believe information cannot be destroyed. Not because unitarity is aesthetically pleasing, not because quantum mechanics happens to be unitary, but because the destruction of information would undermine the very existence of space-time. Information is what space-time is made of. Destroying information would destroy space-time. The error-correcting structure of holographic spacetime makes this explicit. The bulk geometry is encoded in the boundary through a quantum error-correcting code. The code is redundant. Information is distributed across the boundary, protected against local errors. The singularity is a local error in the geometric description, but the information survives the error because the code has enough redundancy to absorb it. The computational complexity perspective, developed by Susskind and others, adds a dynamical dimension. The interior of the black hole grows because the quantum complexity of the state increases. The growth is generated by the boundary computation. The interior is an output of the computation. Information is not destroyed in the interior, because information is what generates the interior. The interior exists because of information. Destroying the information would destroy the interior itself. The Hayden-Preskill protocol shows how information can be recovered from the Hawking radiation. If a quantum bit is thrown into a black hole that is already maximally entangled with the early radiation, the bit can be recovered from the subsequent radiation after just one scrambling time. The black hole is not a vault that locks information away. It is a processor that scrambles information and returns it. The death of information is avoided because the black hole's processing is reversible. The recovery is possible because the information is encoded in quantum correlations between the early and late radiation. These correlations are invisible to any local measurement. They can be accessed only through extremely complex measurements that correlate widely separated quanta. The information is hidden in the correlations, encrypted by the scrambling process, but always present, always recoverable in principle. The page curve is the informational proof of life. The entropy of the radiation rises during the first half of evaporation, as Hawking predicted. Then, at the page time, it begins to decrease. The decrease is the signal that information is emerging. The correlations between early and late radiation grow, encoding more and more of the original information. By the time evaporation is complete, the radiation is in a pure state, containing all the information. The death of information has been averted. The seventh proposal involves quantum error correction and emergent spacetime. Research by Daniel Harlow, Fernando Pastovsky, Benny Yoshida, John Preskill, and others showed that the holographic encoding of spacetime has the structure of a quantum error-correcting code. The bulk spacetime is redundantly encoded in the boundary, protected against local errors. Information in the bulk is not localized at a single point. It is distributed across the boundary, spread out, redundantly encoded, protected. Near the singularity, the error-correcting code degrades. The encoding becomes unreliable. The geometric description breaks down. But the information itself, encoded on the boundary, is not destroyed. The code that generates the geometric description fails, but the information remains in the boundary. The death of information at the singularity is the death of the geometric description, not the death of the information itself. The math is striking. The error-correcting interpretation shows that the information about the interior is not stored in the interior. It is stored on the boundary, redundantly, in a code that can tolerate local errors. The singularity is a local error, a breakdown of the geometric code, but the information survives the error because the code has enough redundancy to absorb it. The eighth proposal involves the gravitational path integral and replica wormholes. Recent work by Pennington, Almheri, Hartman, Maldacena, and others showed that the gravitational path integral, when it includes contributions from replica wormholes, automatically reproduces the page curve. The replica wormholes are saddle points of the path integral that connect different copies of the spacetime. Their contribution ensures unitarity and information preservation. The replica wormhole discovery has additional implications for the fate of information. The gravitational path integral, when performed with proper care, naturally includes saddle points that correspond to replica wormholes connecting different copies of the spacetime. These saddle points are responsible for reproducing the page curve and ensuring unitarity. Without them, the path integral gives the Hawking answer: information dies. With them, it gives the correct answer: information lives. The existence of replica wormholes suggests that the quantum theory of gravity naturally includes non-perturbative effects that save information. These effects are invisible in the semi-classical approximation. They become important only when the entanglement between the black hole and the radiation reaches a critical level at the page time. The death of information was predicted by the semi-classical approximation. The preservation of information is ensured by the non-perturbative effects that the semi-classical approximation misses. The connection between the island formula and the holographic principle is direct. The islands are regions of the bulk that belong to the radiation rather than the black hole in the holographic encoding. The growth of the islands during evaporation corresponds to the transfer of holographic information from the black hole to the radiation. The death of information is averted by the holographic transfer. The black hole complementarity framework, while requiring modification after the firewall argument, still provides an important perspective. The outside observer sees information preserved on the horizon and returned in the radiation. The falling observer sees information falling toward the center. Both descriptions are valid within their own domains. The death of information is observer-dependent. It appears to occur from the inside perspective, but does not occur from the outside perspective. The Planck star hypothesis, proposed by Carlo Rovelli and Francesca Vidotto within the loop quantum gravity framework, offers a concrete picture of what replaces the singularity. The singularity is replaced by a compact object at the Planck density, roughly 5.1 times 10 to the power of 96 kilograms per cubic meter, with a radius of roughly the Planck length. The Planck star preserves information because the matter bounces at the Planck density rather than being compressed to infinite density. The information passes through the Planck scale bottleneck and re-emerges on the other side, eventually released through the white hole transition. The black-to-white hole transition connects the death of information to the birth of information. The matter that collapsed and was apparently lost re-emerges through the white hole, carrying its information content with it. The death was never permanent. It was a transition, a passage through the Planck scale, a temporary hiding that ends when the white hole forms. The connection between all proposals and the Planck scale as the resolution point is one of the strongest pieces of theoretical evidence. Every approach identifies the same scale. Every approach replaces the classical singularity with something finite at that scale. Every approach preserves information. The convergence is powerful. The convergence of all these proposals is remarkable. Every approach, from every direction, arrives at the same conclusion. Information does not die at the singularity. The classical prediction of information death is an artifact of the semi-classical approximation. The full quantum theory preserves information. The mechanisms differ, the details differ, but the conclusion is universal. The connection between all these proposals and the Planck scale deserves emphasis. Every serious approach to quantum gravity identifies the Planck scale as the resolution point. String theory says the singularity is resolved at the string scale, close to the Planck scale. Loop quantum gravity says the bounce occurs at the Planck density. The holographic principle says the fundamental degrees of freedom are counted in Planck units. Causal set theory says spacetime is discrete at the Planck scale. Asymptotic safety says the gravitational coupling reaches a fixed point at Planck energies. The Planck density, roughly 5.1 times 10 to the power of 96 kilograms per cubic meter, is the natural density at which quantum gravity dominates. The Planck length, roughly 10 to the power of negative 35 meters, is the natural scale at which the geometric description breaks down. The Planck time, roughly 10 to the power of negative 43 seconds, is the natural timescale of quantum gravitational processes. The gap between the Planck scale and our experimental capabilities is vast, roughly 17 orders of magnitude. No accelerator can reach Planck energies. No detector can resolve Planck lengths. The study of the death of information must proceed through theory, through mathematical consistency, through the constraints provided by the information paradox itself. The mathematical consistency constraints are remarkably powerful. The requirement of unitarity eliminates many proposals. The requirement of reproducing the Bekenstein-Hawking entropy eliminates others. The requirement of producing the correct low-energy limit eliminates still more. The surviving proposals form a relatively small family. They differ in details but agree on the essentials. Information is preserved at the Planck scale. The thermodynamic constraints are independent and complementary. The four laws of black hole mechanics require consistency with thermodynamics. The Hawking temperature and the Bekenstein-Hawking entropy constrain the internal dynamics. Any proposal that preserves information must also reproduce these thermodynamic properties. The combination of unitarity constraints and thermodynamic constraints narrows the space of possibilities dramatically. The observational constraints from gravitational wave astronomy are tightening. Each black hole merger, detected by LIGO, Virgo, and CAGRA, tests general relativity in the strong field regime. The ring-down signals test the no-hair theorem. Future detectors may detect echoes or anomalies that signal new physics at the horizon. Each observation narrows the range of viable theories. 3's8. The Event Horizon Telescope provides another observational window. The photon ring, if resolved, would encode detailed information about the near-horizon spacetime. If quantum gravity modifies the geometry, the photon ring might reveal the modification. And this is where the answer becomes deeply unsettling, because if information does not die, then the singularity does not do what general relativity says it does. The singularity is not a place where the quantum state is destroyed. It is not a place where the past is erased. It is either not there at all, as the fuzzball program suggests, or it is a breakdown of an emergent description, as the holographic principle suggests, or it is resolved by quantum gravity at the Planck scale, as loop quantum gravity and asymptotic safety suggest. The death of information at the singularity is averted because the singularity itself, as general relativity describes it, does not exist. The deeper truth about the death of information at the singularity is that it reveals information to be more fundamental than spacetime. This is perhaps the most profound and most unsettling implication of the entire information paradox program. Information is not something that lives in spacetime. Spacetime is something that lives in information. The fabric of reality is not geometric, it is informational, and the singularity is the place where the geometric approximation fails and the informational truth shows through. The evidence for this view has been accumulating for decades. The Bekenstein-Hawking entropy scales with area, not volume, suggesting the three-dimensional interior is derived from two-dimensional boundary physics. Mark van Ramsdonk showed that entanglement generates spacetime. The error-correcting code structure shows that spacetime is a redundant encoding of boundary information. The computational complexity growth shows that the interior is generated by quantum computation. Each discovery points in the same direction. Information is primary, spacetime is secondary. Let that sink in. If information is more fundamental than spacetime, then the death of information at the singularity would be worse than a violation of unitarity. It would be the destruction of the foundation from which spacetime itself emerges. Destroying information would be like pulling the threads from which the fabric of space and time is woven. The geometric description would not merely fail at the singularity, it would fail everywhere, because the informational substrate that generates it would have been damaged. This is why most physicists believe information cannot be destroyed, not because unitarity is aesthetically pleasing, but because the destruction of information would undermine the very existence of spacetime. If information dies, the mechanism that generates space and time is compromised. The universe cannot afford to lose information, because information is what the universe is made of. The Bekenstein-Hawking entropy formula, S equals A over 4 in Planck units, is one of the most important equations in physics. It connects gravity through the area of the horizon to thermodynamics through the entropy to quantum mechanics through the Planck units. It is the Rosetta Stone of quantum gravity, and it tells us that the information content of a black hole is finite, well-defined, and proportional to the area of its event horizon. This formula has profound implications for the death of information. It says that the black hole contains a specific, finite amount of information. This information is not infinite. It is not undefined. It is a definite number, calculable from the mass, charge, and spin of the black hole. Any mechanism for information preservation must account for this specific amount. Any mechanism for information death must explain what happens to this specific amount. The formula does not say what happens to the information, but it says how much information there is. The formula also tells us that the information is on the surface, not in the interior. The entropy is proportional to the area of the horizon, not the volume of the interior. If the information were distributed uniformly through the three-dimensional volume, the entropy would scale with volume. The fact that it scales with area suggests that the information is encoded on the two-dimensional boundary. The holographic principle makes this suggestion explicit. The three-dimensional interior is a projection of two-dimensional boundary physics. If the information is on the boundary, then the singularity, which is in the interior, cannot destroy it. The information is not at the singularity, it is on the horizon. The death of information at the singularity is a misconception. The information was never at the singularity. It was always on the boundary, always preserved, always available for recovery through the Hawking radiation. The scrambling time provides a temporal perspective on information dynamics. The black hole processes information at the maximum rate allowed by quantum mechanics. For Sagittarius A star, the scrambling time is milliseconds. Within thousandths of a second of crossing the horizon, the information has been processed, scrambled, and distributed across the entire boundary. The information is not slowly consumed by the singularity. It is rapidly processed by the horizon. The death of information at the singularity is preempted by the life of information on the horizon. The Hayden-Preskill result makes this quantitative. If the black hole is old, already entangled with the early radiation, then a quantum bit thrown in can be recovered from the subsequent radiation after one scrambling time. The recovery is fast. The information emerges quickly. The black hole does not hold information hostage. It processes it and returns it at the maximum speed permitted by quantum mechanics. The connection between information preservation and the arrow of time deserves emphasis. The arrow of time is the direction of increasing entropy. Entropy is an informational quantity. The arrow of time depends on the preservation of information because the second law of thermodynamics depends on the well-defined counting of microstates. If information is destroyed, the counting of microstates becomes ambiguous. The second law becomes ill-defined. The arrow of time becomes uncertain. By preserving information, the universe preserves its own temporal structure. The arrow of time continues to point in a well-defined direction. The second law continues to hold. The thermodynamic framework remains consistent. The Margulis-Levitin theorem sets the maximum rate at which any quantum system can evolve between orthogonal states. Black holes saturate this limit. They process information at the absolute physical maximum. The death of information would require that this maximum rate processor somehow fails, but the Hayden-Preskill result shows that the processor succeeds. Individual bits can be recovered after one scrambling time. The processor works perfectly. Information survives. The preservation of information is not just a principle of quantum mechanics, it is a requirement for the coherence of thermodynamics and the directionality of time. The connection between information and entropy deepens this picture. The second law of thermodynamics says entropy never decreases. Entropy is a measure of the information content of a system, specifically the amount of information required to specify the exact microstate given only knowledge of the macrostate. A system with high entropy has many possible microstates, and specifying which one requires a lot of information. Black holes are the maximum entropy objects for a given mass. The Bekenstein-Hawking entropy of a solar mass black hole is roughly 10 to the power of 77. The total entropy of all black holes in the observable universe is estimated at roughly 10 to the power of 104, dwarfing the entropy of all non-black hole matter at roughly 10 to the power of 88. The entropy of the cosmos is dominated by black holes. The information processing of the cosmos is dominated by black holes. The arrow of time, the direction of increasing entropy, points toward black holes. The thermodynamic future of the universe is increasingly dominated by black holes, and the information that falls into black holes is the information that constitutes the thermodynamic arrow. If that information is destroyed, the arrow of time itself is damaged. The directionality of time depends on the preservation of information, because entropy is an informational quantity, and the arrow of time is the direction of increasing entropy. The scrambling time connects information preservation to the dynamics of the interior. The black hole scrambles information at the maximum rate allowed by quantum mechanics. For Sagittarius A star, the scrambling time is milliseconds. The Hayden-Preskill protocol, published in 2007, showed that if you throw a quantum bit into a black hole that is already maximally entangled with the early Hawking radiation, the information about that quantum bit can be recovered from the subsequent radiation after just one scrambling time. The black hole is not a vault that locks information away forever. It is a processor that scrambles information and returns it, eventually, through the Hawking radiation. The page curve is the informational signature of this process. The entropy of the radiation rises during the first half of evaporation, as the radiation becomes entangled with the remaining black hole. At the page time, the entropy begins to decrease as the radiation becomes progressively purified through correlations with itself. By the time evaporation is complete, the radiation is in a pure state containing all the information that fell in. The island formula reproduces this curve through a gravitational calculation. The quantum extremal islands, regions of the interior that belong informationally to the radiation, grow as the black hole evaporates. More and more of the interior is claimed by the radiation. By the end, the entire interior is part of the radiation system. The information that was in the interior is now in the radiation. Information has been transferred, not destroyed. The connection between the scrambling dynamics and the page curve provides the most complete picture of how information survives. During the first half of evaporation, the black hole scrambles the infalling information and begins to emit it in the Hawking radiation. The early radiation appears thermal because the correlations between early and late radiation have not yet developed. The entropy of the radiation rises. At the page time, roughly the halfway point, the situation changes. The black hole has emitted enough radiation that the correlations between early and late quanta begin to dominate. The entropy of the radiation starts to decrease. Information is emerging. The late radiation is correlated with the early radiation in patterns that encode the original information. By the end of evaporation, the correlations are complete. The radiation is in a pure state. All information has been returned. The island formula provides the gravitational mechanism. Before the page time, there are no islands. The entropy rises. After the page time, islands appear, regions of the interior that belong informationally to the radiation. The islands grow as the black hole shrinks. More and more of the interior is claimed by the radiation. By the end, the entire interior has been transferred. The emergence of the islands at the page time is the key event. It marks the moment when the gravitational calculation switches from the no-island saddle, which gives the rising Hawking answer, to the island saddle, which gives the decreasing page answer. The switch is not imposed by hand. It follows from the gravitational path integral, from the principle that the dominant contribution is the one with the smallest entropy. The recovery of information through the islands is consistent with the Hayden-Preskill protocol. Individual quantum bits can be recovered after one scrambling time, milliseconds for astrophysical black holes. The page curve describes the global recovery over the full evaporation time. The two results are consistent and complementary. The connection between the island formula and the replica wormholes is deep. The replica wormholes are the saddle points of the gravitational path integral that produce the island contribution. They connect different replicas of the spacetime, creating correlations between different copies of the Hawking radiation. These correlations are what ensure unitarity and reproduce the page curve. Without the replica wormholes, the gravitational calculation gives the Hawking answer. With them, it gives the page answer. The replica wormholes save information. This is not science fiction. The island formula is a rigorous result within a well-defined theoretical framework. It has been derived independently by multiple groups using different methods. It is consistent with the holographic principle, with the page curve, with unitarity, and with the thermodynamics of black holes. The connection between information preservation and the nature of consciousness is speculative but worth contemplating. If the universe preserves information perfectly, then the information that constitutes a conscious being, the patterns of neural activity, the configurations of molecules, the quantum states of atoms, is never truly destroyed. When a person falls into a black hole, the information about their physical state is scrambled and eventually returned in the Hawking radiation. The information is preserved, though in a form so scrambled that no practical measurement could recover it. This does not mean that consciousness survives falling into a black hole. Consciousness, whatever it is, depends on the organization of information, not just its existence. The scrambling process destroys the organization while preserving the information content. The distinction between organized information and scrambled information is the distinction between a book and the same letters scattered randomly. Both contain the same information in a technical sense, but only the book is readable. The death of information at the singularity would have been the ultimate erasure, the destruction not just of organization but of the underlying information itself. The preservation of information means that the universe remembers, even if the memory is scrambled beyond any practical recovery. The record exists. The past is encoded in the present, and the present is encoded in the future. The chain is unbroken. The deeper truth is that the death of information at the singularity, the connection between information and reversibility, is central. In classical mechanics, processes are irreversible in practice but reversible in principle. A vase shatters, but reversing every velocity would reassemble it. The information is preserved. 3. The death of information at the singularity would be different, irreversible in principle. No measurement could recover the lost information. The resolution tells us this threat is not realized. Information is never truly lost. It may be scrambled beyond practical recovery, but it is there, always. The universe keeps perfect records. The study of the information paradox has illuminated quantum complexity, the minimum number of quantum operations needed to produce a quantum state. Susskind argued that the interior of a black hole grows because complexity increases. The complexity growth is temporal. The interior is generated by the computation. Information is processed by this computation, scrambled and redistributed but never destroyed. The Hayden-Preskill thought experiment illustrates information preservation sharply. If you throw a quantum bit into an old black hole, one already maximally entangled with the early radiation, the bit can be recovered from subsequent radiation after one scrambling time. The recovery requires complex measurements correlating many quanta, but it is possible in principle. The information is encoded in the correlations, waiting to be extracted. The black hole is not a destroyer. It is a scrambler, the fastest scrambler in nature. It converts organized information into maximally scrambled information. The scrambling is reversible. The information survives. The connection between the information paradox and the multiverse is speculative but relevant. String theory's landscape of vacua may be constrained by the requirement that every vacuum-permitting black holes must also permit information preservation. This constraint may significantly reduce the number of viable vacua. The concept of the page curve as a diagnostic tool deserves emphasis. The page curve is the specific pattern of entropy that distinguishes unitary evolution from non-unitary evolution. Rising entropy during the first half of evaporation is consistent with either. Falling entropy during the second half is the signature of unitarity. The island formula reproduces the falling phase. The gravitational calculation, when performed correctly, gives the unitary answer. Information survives. The page curve proves it. The concept of the quantum extremal island as a transfer mechanism is equally important. The islands are regions of the interior that belong informationally to the radiation. They grow as the black hole evaporates. More interior is claimed by the radiation. By the end, everything has been transferred. The death of information is averted by a gradual transfer from interior to exterior, mediated by quantum extremal surfaces. Was never a prediction of the fundamental physics. It was a prediction of the semi-classical approximation, an approximation that treats gravity classically while treating matter quantum mechanically. When gravity is treated quantum mechanically, through the holographic principle, through the island formula, through the gravitational path integral with replica wormholes, information is preserved. The singularity, where general relativity says information dies, is replaced by something finite and well-defined in the quantum theory. The replacement may be a fuzzball, a quantum bounce, a holographic projection, or something else entirely, but whatever it is, it preserves information. The death of information at the singularity was always an illusion, a consequence of applying a classical approximation to a quantum situation. The full quantum theory, whatever its precise form, saves information. The connection between information and geometry, established through the work of Ryu, Takayanagi, Van Ramsdonk, Maldacena, Susskind, and others, provides the most concrete framework for understanding why information does not die. The Ryu-Takayanagi formula proposed in 2006, relates the entanglement entropy of a region of the boundary theory to the area of a minimal surface in the bulk. This formula connects quantum information on the boundary to geometry in the bulk. It tells us that the geometry of spacetime is encoded in the entanglement structure of the boundary quantum state. The quantum version of the Ryu-Takayanagi formula, developed by Engelhardt and Wall, includes quantum corrections and leads directly to the island formula. The quantum extremal surface, which generalizes the Ryu-Takayanagi surface to include quantum corrections, is the key ingredient. When applied to black hole evaporation, it produces the Page curve and confirms information preservation. The formula tells us that the death of information would correspond to a discontinuity in the geometry. If information were destroyed, the entanglement entropy would not follow the Page curve. The bulk geometry would not be consistent with the boundary theory. The holographic correspondence would break down. The death of information is not just a violation of unitarity, it is a violation of the holographic principle. It is inconsistent with the connection between information and geometry that has been established through decades of rigorous mathematical work. The error-correcting structure of holographic spacetime, discovered by Harlow, Pastovsky, Yoshida, and Preskill, provides the mechanism by which information is protected from the singularity. The bulk information is not localized at a single point. It is distributed across the boundary, redundantly encoded, protected against local errors. The singularity is a local error in the geometric code. But the information survives because the code has enough redundancy to absorb any local error, including the singularity. The computational complexity perspective adds a dynamical element. The interior of the black hole grows because the quantum complexity of the state increases. The growth is generated by the ongoing computation of the boundary theory. The information that fell in is being processed, scrambled, transformed. The processing generates the interior geometry as one of its outputs. The information is not destroyed in the interior. It is what generates the interior. The Hayden-Preskill result makes the recovery of information concrete. If a quantum bit falls into an old black hole, one that is already entangled with the early radiation, the bit can be recovered from the subsequent radiation after one scrambling time. The recovery requires complex measurements that correlate many quanta of radiation, but it is possible in principle. The information is there, encoded in the correlations, waiting to be extracted. The Page curve provides the global picture. The entropy of the radiation rises during the first half of evaporation as the radiation becomes entangled with the remaining black hole. After the Page time, the entropy decreases as the radiation becomes progressively purified through correlations with itself. By the end, the radiation is in a pure state. All information has been returned. The island formula provides the gravitational calculation that reproduces the Page curve. The quantum extremal islands, regions of the black hole interior that belong informationally to the radiation, grow as the black hole evaporates. The islands are the mechanism by which the interior information is transferred to the radiation. By the end of evaporation, the entire interior has been claimed by the islands. All information has been transferred. Let that sink in. The universe does keep perfect records. The past is permanent. Information is indestructible. The death of information at the singularity is averted, not by a minor correction, but by a complete revision of our understanding of what spacetime is and what information is. Spacetime is emergent. Information is fundamental, and the singularity is where this truth becomes unavoidable. What does it mean that information is more fundamental than spacetime? What does it mean that the death of information at the singularity is averted not by a fix within general relativity, but by a revolution that makes information the foundation of physics? It means that the universe is, at its deepest level, an information processing system. The matter and energy that we observe, the spacetime through which they move, the forces that govern their interactions, all of these emerge from an underlying informational substrate. The substrate is quantum mechanical. It obeys the laws of quantum information theory, and it preserves information perfectly, without exception, without loss, for all time. This is a paradigm shift comparable to the shift from Newtonian mechanics to relativity, or from classical physics to quantum mechanics. In the Newtonian paradigm, the universe is a machine. In the quantum paradigm, the universe is a probability distribution. In the information paradigm, the universe is a computation. The fundamental entities are not particles, or fields, or spacetime points. They are bits of quantum information, qubits, whose entanglement patterns generate the geometry of spacetime and whose dynamical evolution generates the flow of time. There is a philosophical pause required here. The information paradigm does not merely add a layer to our understanding of the universe. It changes the foundation. It tells us that the questions we have been asking, questions about the structure of spacetime, about the nature of gravity, about the fate of the singularity, are secondary questions. The primary questions are about information. How is information encoded? How is it processed? How is it preserved? How does its entanglement structure give rise to the emergent geometry of spacetime? The study of the death of information at the singularity has driven some of the most important theoretical advances of the past 50 years. The information paradox launched the field of black hole thermodynamics. The holographic principle transformed our understanding of the relationship between gravity and quantum mechanics. The ADS-CFT correspondence became the most powerful computational framework in theoretical physics. The firewall paradox sharpened the crisis and drove the development of the island formula. Quantum error correction, inspired by holographic spacetime, is essential for building fault-tolerant quantum computers. The mathematical tools developed for these problems have found applications across physics. The ADS-CFT correspondence has been applied to condensed matter physics, nuclear physics, and fluid dynamics. The thermodynamics of black holes has illuminated the physics of strongly coupled quantum systems. Quantum information theory, developed in part to understand the information paradox, underlies the entire field of quantum computing. The observational landscape continues to evolve. Gravitational wave detectors have observed roughly 90 events. The Event Horizon Telescope has photographed 2 supermassive black hole shadows. Future detectors will push sensitivity further. The photon ring may be resolved. Space-based detectors like LISA will detect supermassive mergers. Each observation constrains the range of viable theories and narrows the space of possible resolutions. The relationship between the information paradox and practical quantum computing deserves emphasis. Quantum error correction, the technology essential for building fault-tolerant quantum computers, was directly inspired by the holographic encoding of spacetime discovered through the study of the information paradox. The mathematical tools developed for understanding how information survives in black holes have found direct applications in protecting quantum information in quantum computers. The most abstract question in physics has generated one of the most practical technologies of the 21st century. The philosophical implications of information preservation are profound. If information is indestructible, the universe is a more coherent place than the classical picture suggested. The past is permanent. The cosmic ledger is balanced. Every event leaves an indelible mark. The universe is a perfect accountant, tracking every bit of information with infinite precision, preserving every quantum correlation across all of space and time. This has implications for the nature of reality itself. If information is more fundamental than space-time, then reality is informational at its deepest level. The fabric of the universe is not geometric. If it is informational, the particles, forces, and fields that we observe are patterns in the information. Space-time is a pattern. Gravity is a pattern. The singularity, where general relativity says information dies, is a pattern that breaks down, revealing the informational substrate beneath. The practical technologies that have emerged from this program are already transforming the world. Quantum error correction is the foundation of fault-tolerant quantum computing. The holographic correspondence has provided new computational tools for strongly coupled physics. Gravitational wave astronomy has opened a new observational window. Each of these applications was driven, directly or indirectly, by the attempt to understand whether information dies at the singularity. The practical implications of the information paradigm are already being felt. Quantum error correction, inspired by the holographic structure of spacetime, is essential for building fault-tolerant quantum computers. The connection between entanglement and geometry has opened new approaches in condensed matter physics. The thermodynamics of black holes has illuminated the physics of strongly coupled quantum systems. The island formula has provided new computational tools for quantum field theory. The observational implications are more distant but equally profound. If information is preserved during black hole evaporation, the Hawking radiation carries subtle quantum correlations that encode the information about what fell in. These correlations are in principle detectable, though in practice the required measurements are far beyond current technology. Future gravitational wave detectors may constrain the near-horizon structure. Future Event Horizon Telescope observations may reveal the photon ring, encoding geometric information about the spacetime near the event horizon. Each observation narrows the range of possible quantum gravity theories and constrains the mechanism by which information is preserved. The study of the death of information at the Singularity has driven some of the most important theoretical advances of the past 50 years. The information paradox launched the field of black hole thermodynamics. The holographic principle transformed our understanding of the relationship between gravity and quantum mechanics. The ADS-CFT correspondence became the most powerful tool in theoretical physics. The firewall paradox sharpened the crisis and drove the discovery of the island formula. Each advance was motivated by the simple question: does information die at the Singularity? The answer, as it emerges from the convergence of multiple independent approaches, is no. Information does not die. The universe keeps perfect records. The laws of physics are reversible. Unitarity holds. The past is permanent. And the Singularity, where general relativity says information is destroyed, is itself an illusion, a feature of an approximate description that breaks down precisely where it matters most. The philosophical implications are equally profound. If information is indestructible, if the past is permanent, if every event leaves an indelible mark on the fabric of reality, then the universe is a more coherent, more ordered, more structured place than the classical picture suggested. The death of information would have introduced genuine randomness into the universe, a fundamental erasure that could never be undone. The preservation of information means that the universe, at the deepest level, is deterministic in the quantum mechanical sense. The quantum state, at one time, uniquely determines the state at all other times. The arrow of time exists, entropy increases, but the information is always there, scrambled and redistributed but never destroyed. The next generation of observations will push our understanding further. Gravitational wave detectors, both ground-based and space-based, will detect more events with greater precision. The Event Horizon Telescope will sharpen its images. Future observations may resolve the photon ring, a sharp, bright feature near the event horizon that encodes geometric information about the spacetime near the horizon. If quantum gravitational effects modify the near-horizon geometry, the photon ring might carry the signature. The space-based gravitational wave detector LISA, planned for the coming decades, will detect supermassive black hole mergers. The ring-down signals from these mergers test the no-hair theorem with extraordinary precision. Any deviation from the predicted frequencies could provide a clue about the nature of the interior and the fate of information at the center. The study of the death of information at the Singularity has also revealed unexpected connections between physics and other fields. The holographic principle connects gravity to information theory. The ADS-CFT correspondence connects gravity to quantum field theory. The error-correcting structure of spacetime connects gravity to quantum computing. Each connection was unexpected and was driven by the information paradox. The attempt to understand whether information dies has been one of the most productive catalysts for interdisciplinary advance in the history of science. The practical technologies emerging from this program continue to grow. Quantum error correction for fault-tolerant quantum computing, holographic methods for strongly coupled physics, scrambling dynamics for quantum simulation, random quantum circuits for benchmarking quantum processors. Each application traces its origins to the information paradox. The study of the death of information at the Singularity has driven unexpected connections across disciplines. The topological methods that Penrose used for his singularity theorem drew on pure mathematics. The holographic principle connected gravity to information theory. The ADS-CFT correspondence connected gravity to quantum field theory. The error-correcting structure connected gravity to quantum computing. Each connection was unexpected. Each was driven by the information paradox. The singularity problem has been one of the most productive catalysts for interdisciplinary advance in the history of science. It has brought together general relativists and particle physicists, string theorists and quantum information scientists, mathematicians and computer scientists, all focused on the single question: does information die? The result has been a flowering of ideas that extends far beyond the original question. The next generation of physicists will have tools we can barely imagine. Quantum computers capable of simulating aspects of quantum gravity, gravitational wave detectors of unprecedented sensitivity, theoretical frameworks more refined than anything available today. The resolution of the information paradox, when it comes, will transform our understanding of everything. The relationship between the information paradox and practical quantum computing deserves emphasis. Quantum error correction, the technology essential for building fault-tolerant quantum computers, was directly inspired by the holographic encoding of spacetime discovered through the study of the information paradox. The mathematical tools developed for understanding how information survives in black holes have found direct applications in protecting quantum information in quantum computers. The most abstract question in physics has generated one of the most practical technologies of the 21st century. The philosophical implications of information preservation are profound. If information is indestructible, the universe is a more coherent and more ordered place than the classical picture suggested. Every event leaves a permanent mark. Every interaction creates correlations that persist forever. The cosmic ledger is perfectly balanced. Nothing is lost. Nothing is gained. The total information content is conserved. The universe is the ultimate closed system, and in a closed system, information is conserved by the most fundamental law of quantum mechanics. The death of information at the singularity would have been the first and only exception to this law. The resolution of the information paradox tells us that there are no exceptions. The law is absolute. The universe is a perfect accountant. This has implications for the nature of existence itself. If information is the fundamental substance of reality, if space-time emerges from information, if gravity emerges from entanglement, if time emerges from computation, then the universe is, at its deepest level, an information processing system. The particles and forces and fields that we observe are patterns in the information. The space-time in which they move is generated by the information. And the information is permanent, indestructible, preserved by the most fundamental laws of physics. This preservation is not an approximation, it is exact. It is guaranteed by the mathematical structure of quantum mechanics. It holds in every experiment ever conducted, every observation ever made, and at the center of every black hole where general relativity predicted it would fail. The conservation of information is the deepest law in physics. And the information paradox, which for 50 years appeared to threaten this law, has instead confirmed it to be even more fundamental, even more powerful, and even more inviolable than anyone had imagined. The death of information was never real. It was always an illusion, cast by the shadow of a classical approximation on the wall of our understanding. When we look behind the shadow, we find the information intact, encoded in the quantum correlations of the cosmos, preserved forever by the unbreakable laws of quantum mechanics. We are beings made of information. Our bodies are configurations of atoms. Our minds are configurations of neurons. Our memories are patterns of synaptic connections. And if the universe preserves information perfectly, then the information that constitutes us, the information that makes us who we are, is permanent, not in the sense that we are immortal, but in the sense that the information is never lost. It is scrambled, redistributed, hidden in the quantum correlations of the cosmic microwave background and the Hawking radiation and the entanglement structure of the universe. But it is there, always, permanently. The universe remembers. The death of information at the singularity was the most important crisis in the history of physics. It pitted the two greatest theories of nature, general relativity and quantum mechanics, against each other in the most direct and irreconcilable conflict. General relativity said, information dies. Quantum mechanics said it cannot. One of them had to be wrong. The resolution, as it is emerging from the convergence of multiple theoretical approaches, is that general relativity is wrong, at the singularity, not everywhere, not at everyday scales, not in the regime where it has been tested with extraordinary precision, but at the singularity, where the curvature reaches the Planck scale and quantum gravitational effects become dominant. The classical prediction of information death is an artifact of an approximation that has been pushed beyond its limits. Information does not die, it is preserved. The universe keeps perfect records. The past is permanent. Unitarity holds. The laws of physics are reversible. The death of information at the singularity was always an illusion, a shadow cast by the semi-classical approximation on the wall of our understanding. When we look behind the shadow, we find information preserved, encoded in the quantum correlations of the Hawking radiation, stored on the holographic boundary, protected by error-correcting codes, connected through wormholes of entanglement, processed at the maximum rate allowed by quantum mechanics. Every great revolution in physics has been triggered by a crisis in our understanding of fundamental principles. The ultraviolet catastrophe led to quantum mechanics. The incompatibility of Maxwell's equations with Galilean relativity led to special relativity. The incompatibility of Newtonian gravity with special relativity led to general relativity. The death of information at the singularity is the latest and deepest such crisis, and the revolution it is driving will be the most profound yet. The resolution requires quantum gravity, a theory that unifies general relativity and quantum mechanics into a single framework. Every candidate for quantum gravity, string theory, loop quantum gravity, holographic duality, causal set theory, asymptotic safety, agrees that information is preserved. The mechanisms differ, the mathematical frameworks differ, but the conclusion is universal. The theory of quantum gravity will tell us what replaces the singularity. It will tell us how information is encoded on the boundary. It will tell us how it escapes through the Hawking radiation. Encoded. Encode. It will tell us what spacetime is made of. It will tell us what reality is at the deepest level. And the key to all of these answers is the information paradox, the crisis that launched the revolution. The answer is emerging, not complete, not final, but clear in its direction. Information does not die, it is preserved. The singularity is not a graveyard, it is a placeholder for physics we do not yet understand. And the physics we do not yet understand, quantum gravity, will reveal that the universe is a more perfect, more coherent, more beautiful place than we imagined. The crisis is not fully resolved. The mechanisms are not fully understood. The precise form of quantum gravity remains unknown. But the direction is clear. Information survives. The singularity does not destroy it. The fuzzball absorbs it. The holographic boundary encodes it. The island formula transfers it. The page curve confirms it. The error-correcting code protects it. The wormhole network connects it. The computation processes it. The universe preserves it. The death of information at the singularity was the question that launched a revolution. The revolution in our understanding of spacetime, information, holography, entanglement, and the nature of reality. The question was, does information die? The answer is no. And the path to that answer has revealed that information is not a passenger in the universe. It is the universe. The fabric of spacetime is woven from information. The flow of time is generated by information. The structure of reality is built from information. The singularity, where general relativity said information dies, is the place where this truth is most clearly revealed. The geometric description fails. The classical approximation breaks. And through the cracks, the informational foundation shows through. The deepest truth about the universe is not geometric, it is informational. And the death of information at the singularity which for 50 years threatened to undermine the foundations of physics, has instead revealed those foundations to be stronger, deeper, and more beautiful than anyone imagined. Information does not die, not at the singularity, not anywhere, not ever. The universe is a perfect record keeper. And the record it keeps is the record of everything that has ever happened, encoded in the quantum correlations of every particle, preserved by the laws of physics that govern their evolution, and stored in the fabric of reality itself. The resolution of the information paradox is one of the great intellectual achievements of the past decade. The island formula, the page curve, the replica wormholes, the holographic encoding, the error-correcting structure, the scrambling dynamics, all of these pieces have come together to form a coherent picture of how information survives. The picture is not yet complete. The precise mechanism of information recovery is not yet understood. The theory of quantum gravity that underlies all of these results has not yet been written, but the direction is clear and the conclusion is firm. Information does not die. The record is complete, the record is permanent, and the record, when we finally learn to read it, will tell us everything there is to know about the nature of existence. The death of information at the singularity was the question. The preservation of information is the answer. And the path from question to answer has revealed that the universe is a more subtle, more beautiful, and more coherent place than anyone imagined when Hawking first posed the paradox in 1975. Every revolution in physics has been triggered by a crisis. The ultraviolet catastrophe led to quantum mechanics. The incompatibility of electromagnetism with Galilean relativity led to special relativity. The information paradox has led to the information revolution, the deepest revolution yet, the revolution that reveals information to be the fundamental substance of reality. The theory of quantum gravity, whatever form it takes, will be a theory of information. It will describe how information is encoded, processed, scrambled, and recovered. It will describe how entanglement generates geometry. It will describe how computation generates time. It will describe how the universe remembers everything that has ever happened. The singularity was never a graveyard for information. It was always a signpost, pointing toward the deeper truth, that information is indestructible, that the universe keeps perfect records, and that the fabric of reality is woven from quantum bits whose preservation is guaranteed by the most fundamental laws of physics. The search for the theory of quantum gravity continues. The constraints are tightening, the proposals are converging, the observations are accumulating, and the answer, when it finally comes, will tell us not just what happens to information at the center of a black hole, but what information is, what spacetime is, and what reality is at the deepest level. The history of physics is a history of crises resolved by revolutions. The ultraviolet catastrophe led to quantum mechanics. The failure of Galilean relativity led to special relativity. The failure of Newtonian gravity led to general relativity. The death of information at the singularity is the latest crisis. And the revolution it is driving, the information revolution, the realization that information is the fundamental substance of reality, will be the deepest revolution yet. The answer is taking shape. The island formula reproduces the page curve. The holographic principle preserves information on the boundary. The error-correcting code protects it from the singularity. The computational complexity generates the interior. The wormhole network connects interior to exterior. The scrambling dynamics process information at the maximum rate. Every thread of the tapestry is being woven. The picture is emerging from the darkness. The answer is emerging from the convergence of multiple theoretical frameworks, constrained by the consistency requirements of quantum mechanics, thermodynamics, and the holographic principle. The answer is, information lives. The universe is a perfect record keeper. The past is permanent. The laws of physics are reversible. Unitarity holds. And the singularity, where general relativity said information dies, is itself an illusion, a feature of a classical approximation that breaks down precisely where it matters most. The information lives, it has always lived, it always will, and the universe, at its deepest level, is nothing more and nothing less than the eternal preservation of that information.